Hi, welcome to section 7.3, the central limit theorem. So in this section, we're going to identify the conditions needed to apply the central limit theorem, and then we're going to use that central limit theorem to find probabilities. So in front of you right now, you should have the 7.3 video notes printout, and you should also have the standard normal table that was sent to you with the chapter 6 notes. So in this one section, 7.3, you're actually going to be using pretty much everything that you've learned from chapters 1 through 6. So here we go. So the central limit theorem is used to estimate proportions in a population, and it also tells us that if some basic conditions are met, the sampling distribution of the sample proportion is close to the normal distribution. So this is what's important about the central limit theorem. Up until this point, problems that we've been doing has been telling you that the distribution is approximately normal. So from here on out, we're going to have to figure that out first. So we're going to have to figure out, is this distribution normal? Normal being looking like that. And if it is normal, then we can continue. If not, then we would go about it in a different way. So if we take a random sample from a population and find that the sample size is large and the population size is large enough, then the sampling distribution of p hat is approximately normal with a mean of p and a standard deviation of the standard error. So remember before when we wrote a normal distribution, we would write it this way, capital N showing that it's normal, and then we would list the mean and then the standard deviation. So same thing here, except once we find out that it is normal, we're going to use p, because remember, p is like the mean, your population proportion, and we're going to use standard error, which is like standard deviation. So when you see it written this way, this is telling you it's normal distribution. Here's where p is, and here's the standard error. And if you don't know what the value of p is, because remember oftentimes we don't know the entire population, then we can substitute it with p hat. Okay, so here are the conditions for the central limit theorem, and there's 3 of them that need to pass. So number 1, the sampling is random and independent. So when we see in a problem, they say based on random assignment, then we know that it is not biased, right? So that we know it's random. And if it is random, we're just going to assume that it's independent as well. Okay, and the second one, large sample size, right? These come from the gold standard as well. So large sample size, previously we were thinking that, okay, it has to be large, but we didn't have an actual way to calculate if it in fact was large enough. So here's how you would calculate it. The sample size, n, is large enough that the sample expects at least 10 successes and 10 failures. Successes meaning the probable outcome that we're looking for, and failures being its complement. So if, for example, p hat was, I don't know, 20%, 0.20, then we know its complement, the 1 minus p hat, would be 0.80. So both of those sides, we need to get the proportion of that is greater than or equal to 10. And number 3, we want a big population. So if sampling is done without replacement, the population must be at least 10 times larger than the sample size. So for population, remember, oftentimes we don't actually know the amount in the population, like we don't know the actual amount of fish in the ocean, but we can make assumptions as to how much fish there are in the ocean to determine if it is 10 times larger than a sample size. Okay, so here is an example of central limit theorem for sample proportions. This figure shows the sampling distribution of p hat for 10,000 samples of size 10, drawn from a population with p at 0.25. Note that this does not satisfy condition number 2 of the central limit theorem because the sample size is too small and the distribution is not normal. And let's go ahead and calculate what the condition number 2 would look like to show us why that sample size is too small. Okay, so we're going to go ahead through the sample or central limit theorem condition number 2 to test the sample size of 10. We know that the sample size is 10. Remember, this is a sampling distribution, right? So this is many, many samples over and over and over again. But right here is sample size of 10. So we need to calculate the successes and the failures. Okay, so here is how we're going to calculate successes and failures. We're going to take the sample size of 10, multiply it by our p, our proportion of 0.25, and that needs to come out greater than 10. But as you can see, it's not going to, because 10 times 0.25 gets us to 2.5, which is less than 10. So that one doesn't work out. And the failures doesn't work out either, because if our successes is 0.25, we know that the failures is 0.75. 10 times 0.75 gets us to 7.5. So both successes and failures do not work, telling us that the sample size of 10 is too small. And we can verify that when we look at this distribution, you can clearly see that the distribution has like a tail on the right side, which indicates that it's kind of more skewed rather than normal. Okay, so let's do another example to show the sample size. This figure shows sampling distribution of p hat for 10,000 samples, so that's the same, but now it's size 100, so the sample size is 100. Drawn from a population with proportion at 0.25, that's the same. And it says, note, this does satisfy the sample size condition, and the shape of the distribution is approximately normal. So let's go through that sample size check of successes and failures. Okay, so here's how it looks set up. Now we're going to input the sample size of 100 and multiply that by the proportion, which is p, of 0.25. You can see that 100 times 0.25 gets us to 25. That's greater than 10, so that works. Successes works. As far as the failures, same size of sample 100, but now if the successes is 0.25, again, the failures is 0.75. 100 times 0.75 gives us 75. So we know the failures works out as well. So if the other two conditions, 1 and 3, work out, that would then tell us that the distribution is normal. And you can see that this distribution looks more tightly clustered based on the larger sample size, giving us a normal distribution. Okay, so now that we have that to be normal, you can figure out the standard error. Remember, this is how you would calculate standard error. Okay, so that's the formula for standard error. And notice that in the calculation down at the bottom, we have p times 1 minus p. What are those? Those are just successes and failures. Successes is 0.25, failures at 0.75, right? Remember, those are always complements. Then we divide it by sample size of 100. So now that you have standard error, you can write it out like this, showing that it is a normal distribution, and that p, your proportion, is 0.25, and standard error is 0.0433. 5%. Okay, so here are our first example. According to www.statisticbrain.com, 59% of vegetarians are women. Suppose a random sample of 500 vegetarians is taken. What is the approximate probability that the proportion of females in our sample will be more than 63%? So let's figure out what we got here in the problem. So I see this sample of 500, and I see this 59% of vegetarians. So this 59% question here, is it P or is it P hat? Well, because it's coming from the entire population, this represents P. And so what is the entire population? Right now it doesn't give us a value for that, but we're going to say the population here is all vegetarians, because that's what we're talking about. And so the question is asking right here, what is the approximate probability that the proportion of females in our sample will be more than 63%? So they're asking about P hat. What is P hat? Is it coming out more than 63%? Okay, so let's go through the central limit theorem conditions. Condition number 1, is it random? I see that it says random sample right there. So random, we're going to put a check. Condition 2 is sample size. sample size, remember we have to check the successes and we have to check the failures. Okay, so successes, sample size we have is 500. Proportion is 0.59. And 500 times 0.59 gets you to 295. Is that greater than or equal to 10? Yes. We're going to put a check by successes. For failures, sample size of 500. Proportion of failures would be 0.41 if the successes is 0.59. And 500 times 0.41 comes out to 205, which is greater than 10. So we'll put a check by the failures as well. Third condition that we're checking for central limit theorem is your population size. Has to be 10 times your sample size. So our population right now is all vegetarians. We don't know the actual value, but do we think that all vegetarians is greater than 10 times 500, which is 5,000? We'll just assume that the entire vegetarians in the world is greater than 5,000. So we'll put a check there. And this is what I'm talking about for population that we can assume sometimes. Okay, so now that we know that it is normal, we have the proportion at 0.59, and we're going to find the standard error right now. So standard error, I know this is long, guys, but it has to be done. Okay, so P in our case, we're talking about the proportion of 0.59. 0.59 is the successes, 0.41 is the failures. Sample size here is 500. Inputting this into our calculator all at one time, I'm going to round to 3 values after the decimal place. So we'll get 0.022. So that's this. So here's what we're working with. If at this point you need to kind of like rewind and listen to this again to get all your notes or to get this sunken in your head, go ahead and do it, because this is super, super important that you understand all of these pieces in this slide right here. Okay, so now that we know it's a normal distribution, let's actually answer the question, because we still didn't even answer the question yet. All we really did was know that the distribution is normal by going through the CLT conditions. So what is the approximate probability that the proportion of females in our sample will be more than 63%? So let's go ahead and draw the picture. Okay, so I'm going to make my drawing based on normal distribution, P at 0.59, standard error at 0.022. Okay, so there's a normal distribution using P at 0.59, standard error of 0.022. And remember, this is of the sampling distribution. So what's the probability of it being more than 63%? So let's go ahead and mark out that area. Okay, so we know that we're looking for this right side, finding more than 63%. So remember from here, this is what we did in chapter 6. Okay, so from here, what we want to do is find the z-score. But remember now, z-score is not in terms of mean and standard deviation, but it's in terms of p hat, and standard error. Right, so now this is what we're using to calculate the z-score. Instead of x, we're using p hat. Instead of the mean x bar, we're using p. And instead of standard deviation, we're using standard error, because now we're talking about a sampling distribution. So let's go ahead and fill this out. Okay, so I have this formula filled out. Notice that in the denominator for standard error, I didn't just write 0.022 because I want to ensure that I'm not using rounded values to calculate, because oftentimes that standard error value, the number can be very, very long. So I put the whole entire formula for standard error in the denominator to ensure that I'm not using rounded values, and I'm going to calculate all of this at one time. So make sure when you're using a calculator that you use parentheses for the numerator and you're using parentheses for the numerator under the square root as well. This ensures the correct order of operations when using the calculator. This z-score should come out, or does come out, to 1.82. Okay, so once you have this z-score of 1.82, we can go ahead and utilize the standard normal table because we know that it's a normal distribution, right? We can't use that table if we didn't know it was normal. So now we're going to look up z-score of 1.82. And when I look on that standard normal table, you guys can verify this on your table as well. But I find a p-value associated with that z-score of 1.82 at 0.9656. But remember, 96.56, that's a big area. What we just found was the left side, right? We want the right side. So we'll just go ahead and find its complement and subtract it from 1. Okay, so I went ahead and subtracted it from 1. We came out with 0.0344. And if we look at it as a percent, it's 3.44%. And that represents this area right here. So what is the approximate probability that the proportion of females in our sample will be more than 63%? Well, we have a 3.44% chance of there being more than 63% females. Okay, so here's example 2. In a closely contested school bond election, polling indicates that 50% of voters are in favor of the bond and 50% are against the bond. Suppose a random sample of 80 voters is selected. What percentage of the sample would we expect to favor? Number 2, does the central limit theorem apply? Number 3, what's the standard error? And number 4, what's the approximate probability that the sample proportion will fall within 2 standard errors of the population value of 0.50? Okay, so based on this information, we know that our sample size, first of our sample, we know that it's random, right? And we know that the sample size is 80. And we also know that P is 0.5. So based on this information, I would pause this video right now before I show you the answers, and then try to see if you can calculate all of this on your own. So with our sample of 80 people and P at being 0.50, question number 1 asks, what percentage of the sample would we expect to favor? Well, if we do this in an accurate and precise way, remember from section 7.1 and 7.2, what do we expect? Well, for P hat, we expect it to be the same as P. So we also expect it to be 50%. So number 2, the question is, does the central limit theorem apply? So we'll go through central limit theorem conditions. Number 1, first condition, remember, is it random? It said it was a random sample of 80, so check. Number 2, sample size, successes, failures. So our sample size of 80, proportion of 50%. 50% of 80 is 40, which is greater than 10. So successes is a check. Failures, if successes is 50, failures is 50. So we also come out for the failures at 40, which is greater than 10. So our sample size is large enough. Lastly, we're checking population to be greater than 10 times our sample size. Let's see, our population, we're going to assume that there are more than 800 voters for this district. So population check. And then the last question they were asking for standard error. So standard error here, P is 0.50, sample size of 80. So for standard error, this comes out to be 0.0559 when you calculate that in your calculator. So we know that it's normal because central limit theorem conditions apply. P came out to be, or was, 0.50, and our standard error here is 0.0559. So since the central limit theorem applies, we can use a normal model for the distribution. That's what we had on our last slide. By the empirical rule, we know that the probability that the sample proportion will fall within two standard errors of 0.50 is 95%. Remember empirical rule 68, 95, 99.7. We could also verify this using technology. Okay, so since we did the central limit theorem, we know that it's a normal distribution. And we need to know it's a normal distribution because in the past we've been using two tools that have been helping us to find probabilities. First tool is what we did in the previous example using the standard normal table. You can only use that table based on a normal distribution. The other tool is empirical rule. Remember 68, 95, 99.7. We can only use empirical rule, again, if it's a normal distribution. Okay, so here is a picture of kind of what's going on. We know that we have markers here at the -2 standard error marker and the +2 standard error marker. And according to empirical rule tells us that within 2 standard deviations of the mean, that is where 95% of the data will lie. So just one iteration though, because we're working with a sampling distribution, we wouldn't say that this right here is X, but we're looking at P right here in the middle. Okay, so to understand further what's happening in this diagram, so we know that from P of 0.5, if we add 2 standard errors, we will get to 0.6, or to be more specific, 0.6118. And that's the marker that we would have on the up tail. Now on the bottom tail, we would do the same thing, except we're going to subtract 2 standard errors. And when we do that, we come out with a number of 0.3882. Notice on the diagram, they rounded that up to 0.4. Well, actually, it is at 0.3882. Yeah, so the marker a little bit before 0.4. And so we know that between 0.3882 and 0.6118, that's where 95% of the data will lie. And so to answer the question, within 2 standard deviations, because we have empirical rule and it makes it so much simpler for us, we can easily answer that as 95%. Okay, last example. According to the American Veterinarian Medical Association, 36.5% of all Americans own a dog. Suppose a random sample of 200 Americans is taken. Would it be surprising to find that 45% of the sample owned a dog? Why or why not? So this question is asking, would it be surprising? Remember from, I don't remember what chapter, but how do we know if something is surprising, or how do we know if something is unusual? Remember we talked about this and we said if something is falling outside of that 95%, it's going to be unusual, because if all the data is falling, or 95% of the data falls within 2 standard errors, it'd be really, really surprising if it fell outside. So not to more than 10. Okay, so here we go. Let's figure out if it's surprising or not. Well, first of all, we need to know if it is in fact a normal distribution, right? So let's go ahead and do central limit theorem conditions. Okay, so I've set up the conditions. Now let's go through and check them off. Well, in the example in the previous slide, it did say that it was based on a random assignment. So we'll go ahead and put a check for random assignment. Number 2, sample size. So we'll check the successes and failures. So we're going to go ahead and check the successes first based on a sample size of 200. P is 0.365. So 200 times 0.365 is 73. So successes checks out. We'll check the failures. Sample size 200. If we do 1 minus 0.365, you get 0.635 as the failures. And when you multiply that by 200, it comes out to 127. So we know that the sample size is large enough. 200 is a good sample size. And then last thing we'll check is the population. It needs to come out more than 10 times the sample size. Well, the population right here, we don't have a number, but we know that it's talking about all Americans, right? So the amount of Americans, do we think that it is more than 10 times 200, which is 2,000? Definitely. We know there's more than 2,000 Americans, so we're going to check that off. Okay, so all conditions of the central limit theorem are met, telling us that it is normal, so we can proceed to find standard error. Okay, so I set up the standard error formula, and I hope you guys can't hear it, but it is raining here, so you might be able to hear some rain in this video. But so standard error, using a proportion of 0.365, and I know from when we did the failures, that came out to be 0.635 here. I'm going to use that number, and we're going to divide that by our sample size of 200. Okay, so when this gets multiplied out, it comes out to 0.034. So I'm going to write here my normal distribution using my capital N, with P being 0.365 and standard error at 0.034. So I can use this to continue. Okay, so let's finish and answer the question. Remember, we're trying to see if we get a p-hat of 0.45, is it surprising? Well, how do we know if something is surprising or unusual? Remember, we did this previously. How do we know something is unusual? Well, we said that if it lands outside of 2 standard deviations, we know it's going to be unusual because most of the data, 95% of it, is within 2. So there's only a 5% chance of landing outside. So let's see if 45% lands outside. Okay, so I have a normal distribution. My P is at 0.365 and my standard error is at 0.034. So if we make a drawing to show this, this is what it's going to look like. Okay, so this is what's kind of going on. Of course, we could find or show where the middle is at 0.365 and keep adding 0.034 until we get to 2 standard above, subtract till we get to 2 standard below. But another way we could do this is just like how we did in the previous example, is where we're taking 0.365, our P, our starting point, and I'm going to add 2 standard errors, and it'll bring me to this marker right here. So when I calculate, I get 0.433, and that tells me that 2 standard errors above the mean is 0.433, and I can get the marker on the lower tail as well by taking 0.365 and subtracting 2 standard errors. And when I do that, I get 0.297. And now that we have these 2 markers, we can estimate, or not estimate, but we can see where this 45% is landing. We see that between -2 and 2 standard errors, it goes from 0.297 to 0.433. So because 0.45 will be outside of that marker over here, we would say yes, that would be an unusual rate.